me a few more seconds to get things set up. I don't have my normal kind of dual screen set up that I normally have in class. Go here. Alrighty. So today we are going to be kind of continuing on with this talk about measurements and the way scientists measure things. And today we're going to be talking about a specific thing that scientists sometimes want to measure about an object, and that is called its density. So can everybody see the density notes on their screen? Okay, a big blue box that says density in it.
Yeah.
Yes.
Yes.
Okay, good. Just wanted to double check and make sure. So density is a sort of combination type measurement that scientists make about objects. It has to do with comparing its volume and its mass. So we talked about mass with the grams and kilograms and stuff like that, and volume with the liters and milliliters on Tuesday. And density is something, it's this type of measurement that brings both of those together. So you've probably heard of like density, like if something's really, really dense, you probably associate it with being like really heavy and hard to pick up. But density isn't just a measurement of heaviness, it's more a measurement of compactness of a material, meaning how much mass, how much material are we able to fit in a certain area, in a certain structure. So it's this sort of measurement of how closely the atoms or molecules in a piece of matter are able to kind of get packed in close to each other. So it's not just heaviness, right? Something can be really, really heavy, but if it's really big, then it's probably not particularly dense. Like I don't know, a refrigerator, right? Refrigerator, very heavy, hard, extremely hard for just one person to pick up and move a fridge around. But a refrigerator is also very large. Part of the reason why it's so heavy is just because it's a big structure. So just because a refrigerator is very heavy doesn't necessarily mean that it is super dense, right? There's literally a big whole open air area in the middle of the fridge where you put your food and stuff if it was plugged in, right? So density is heaviness and volume. So a comparison of how heavy something is compared to how much space that it takes up. So all matter, all substances have density. So solids are obviously fairly dense materials in and of themselves, but liquids can also have different densities, and even gases. So normally we think of gases of being extremely light and extremely like kind of floating around in the air, but they still have a density. Gas is still a type of matter, and all matter has density. So it's this relationship between weight and heaviness versus how much space it takes up, its volume. That's what density is all about. So it's this idea of compactness. So up at the top, we have a less compact material. We have all these different atoms or molecules or particles or whatever they are, and they're all kind of spread out from one another a little bit, right? There's only a couple areas where there's a lot of them overlapping. They're mostly kind of not touching or barely touching other particles that are around them. So this would be a less compact, a lower density material up here. Versus if we compare that to something that has the same amount of particles, but they're all really, really tightly packed in together, really, really close in to one another. They're very compacted down in here. This would be a more compact and therefore a more dense material. So the more compact a material is, the more of it you're able to squish down into a smaller area, the higher the density of your material is going to be. So the kind of more scientific explanation of density is it's the amount of matter per unit volume, meaning it's this ratio of mass and volume. How heavy is it compared to how much space that it takes up? So like, this might be just on my mind because it's trash day for me today, but imagine when you're throwing stuff away in the garbage can, right? Your garbage can is a set volume. It's a set size, right? So you throw away some pieces of trash and it looks like it's starting to get very full. But then as soon as your trash is full, do you immediately take out the bag and tie it up and throw it out into the outdoor garbage? What most people do is you smush it, right? You squeeze that trash down into the bottom so that you can fit more trash on top before you have to take that trash bag out. So if the volume stays the same, like you have your plastic trash bin in your kitchen, but you put more stuff inside of it, you increase the mass, the density of your trash is going to go up, right? You have one set container, one set trash can. It started off with some trash in it, but you squished that trash down and added more and more and more trash. So you have the same volume of trash can, but more trash in there, more stuff. So you just increase the density of the trash in your kitchen, right? You made more mass in the same volume. So you compacted your trash more, you had more particles, quote unquote, of trash. So your density went up. If, however, you take your plastic, like little kitchen trash bag, and you empty out your trash into one of the big, like massive, like 50-gallon trash bags, or like the bags that you use to bag up like leaves and lawn clippings and stuff at the front of your house, one of the really big trash bags, or like one they'd use for one of the big trash cans at like a cafeteria. So if you took your little amount of trash and dumped it into the bigger trash can, the trash would be able to spread out from itself a little bit more, right? The mass stayed the same, so you have the same type of trash, but the volume increases. It went from a little trash can to a big trash can. So in that case, the density of your trash went down. It became less compact. It was able to spread out more. So mass and volume are kind of these two things that we are balancing for density. The heavier that something gets, if the volume stays the same, density goes up. The lighter that something gets, or the more volume that something has, the density is gonna go down. Right? So if you have the same volume, but you cram more and more stuff into there, you're making it more dense. If you take stuff out, or you increase the volume, you put it into a bigger container, the density will go down. It'll be a less dense trash or less dense of whatever it is that you might be working with. So the way that we describe density kind of scientifically or mathematically is this wonderful equation right here. So this slide and the slide after it are probably the two most important slides that we're going to go over for our class today. So we've got density is equal to mass divided by volume. D equals M over V is how you'll see it written out a lot. Mass is usually represented by grams, and volume, a lot of the cases we're talking about solid things. So volume is usually represented by centimeters cubed. It can also sometimes be milliliters or liters. But this is kind of like our unit for density. So like we'd measure the weight of something in kilograms, or we'd measure the height of somebody in meters. we measure the density of a substance in grams per centimeters cubed. It's kind of like how in speed you have miles per hour or kilometers per hour. In density, you have grams per centimeter cubed. Mass per volume. So you take your mass, however heavy that your substance is, you divide it by the volume, however much space that your substance takes up, and you'll be able to figure out the density. So density equals mass divided by volume is kind of our main straightforward go-to of what our density equation is. D equals m divided by v. However, sometimes we know we've already measured maybe density and the mass of something, but we don't know the volume. Or we've measured the density and the volume, but we don't know the mass. So as long as you have two of these three measurements, you can do a little bit of simple math in order to figure out density. So, for example, if we knew the mass of an object and the volume of an object, then we can calculate the density. We do mass divided by volume, and we can calculate density. If we do the mass, if we know what the mass is, and we know what the density is, we can calculate volume. So we do mass divided by density is equal to volume. And then finally, if we know what the density is and we know what the volume is, we can figure out our mass. In this case, we can do D times V, density times volume, in order to figure out the mass. So one way that some people like to kind of think about it is with what's called the DMV triangle or the MDV triangle. And it's this idea that if you know what one of these, or if you're looking for one of these measurements and you have the other two, you can use this little triangle to figure out what the equation is that you need. So for example, if you want to know density, that means that you have mass and you have volume. The triangle says that when you have mass and you have volume, you do some division, mass divided by volume, in order to figure out density. Same thing with if you want to know the volume, but you know what the mass is and you know what the density is, then you can do mass divided by density is equal to our volume. And then finally, if you know, or if you want to know what the mass is, and you know what the density and the volume are, the triangle says do density times volume, and that'll be equal to the mass. So density equals mass over volume. That's kind of like our basic, straightforward density equation. So if you measure the mass and you measure the volume, you can do m divided by v, and it'll tell you the density. But you can also figure out the volume and the mass as long as you have the correct two components. So if you know mass and density, you can do m divided by d to get volume. And if you know density and you know volume, you can do d times v in order to get mass. So as long as you have two of the measurements, you can do one of these equations in order to figure out the final one, in order to figure out the missing one. So this is going to be important for the homework for today and tomorrow, because the homework is either going to want you to calculate density or calculate volume or calculate mass. And it'll give you the other two measurements. And you'll have to know, or you have to come back to the notes and look and see what type of math do you have to do in order to calculate density, volume, or mass. All right, so go ahead and pause it right there. Anybody have any density questions so far? Anything that you're still a little bit confused about with density, or anything about the density equation that you're still a little unsure of?
No, sir.
All right, cool. Thanks, Dewey. So again, as long as you have down that D equals M over V equation and you feel pretty comfortable with that, then you should be in pretty good shape. All right. So density, mass divided by volume. Volume, mass divided by density. Mass, density times volume. So a couple other things that I wanted to go over with you guys about density. That's kind of the most important thing, that density equation. But a couple other things I wanted to mention. Like I mentioned, gases still have density, just like solids and liquids. So in general, the density of gases depends on their volume, right? Gases are all super light. So how much space that they take up will kind of determine what their overall density is. So if you remember, way back at the beginning of the school year, we talked about solids and liquids and gases. And I mentioned that in gases, the particles are very fast, they have a lot of energy, and they're moving around a whole lot. So the more the particles move around, the more kinetic energy that they have. That causes them to be spread out more, be further apart overall, which makes their volume go up. And if you think about our density equation, if your volume is getting bigger, if the number down here is getting bigger, that means that your density is going to get smaller. You're going to have a lower density if you have a really big volume. So the hotter the air, the bigger the volume and the less dense that it is. So cold air is more dense than warm air. Warm air will tend to rise and cold air will tend to sink in the atmosphere. So this is the basic premise behind hot air balloons, right? The reason that the balloon is able to inflate and drift over and through the air is because inside of the balloon, they have that big furnace that you'll see the guy pull on the lever and then the fire will be like, whoosh. That's causing the air inside of the balloon to heat up and get hot. So as the air inside the balloon gets hotter, it becomes less dense, which means it starts to rise above the cooler air that's surrounding it. So temperature can have a big effect on density, especially in things like gases. Liquids also have different densities compared to each other. In general, one good way to figure out how dense a liquid is likely to be is that the more dissolved solids you have in your liquid, so the more particles that are dissolved in the liquids, the more that compounds and atoms that are mixed in, right? So if you have some sort of mixture, if you have a lot of stuff mixed into your liquid, then that liquid is going to be more dense. It has more matter in it than liquid without that stuff. So ocean water, for example, is more dense than lake water or fresh water because it's got all that extra salt that's dissolved in there. Some liquids just also have natural densities to them. So like in our glass right here, we have, it looks like some sort of motor oil on the bottom here. And then some sort of clear liquid in the middle. It might be water, but I think it's something a little heavier than water, maybe like ocean water in the middle. And then up top here, we have some oil. It looks like some vegetable oil. So because the densities of these liquids are different, they sit in different parts of this beaker. The most dense liquids sink down to the bottom, and the least dense liquid floats up to the top. So you'll always have things that are less dense that float on top of things that are more dense. Liquids can also be affected by temperature. So cold water in lakes tends to sink. So the lower you get in the lake, the colder the water tends to go. And as the water warms up, it tends to kind of rise to the top of the lake. So for an example of how this kind of floating action and how these different densities interact with each other, think about this. Mercury is a very dense metal, 13,600 kilograms per meters cubed. So that's pretty high density. And one of the cool things about mercury is that it is a liquid at room temperature. Mercury is one of the few metals that melts at like 75, 80 degrees. So this is a little cup of liquid mercury right here. So it's mercury, a metal that is naturally liquid at room temperatures. Lead is another metal. Lead is not liquid. Lead is a solid. The density of lead is 11,340 kilograms per meters cubed. So mercury is a liquid and lead tends to be a solid. So like a block of lead or like a lead ball, and you dropped it into a vat of liquid mercury, what do you think is going to happen to the lead ball? Is the lead ball going to sink or float on top of the mercury? Randy thinks it's sink. So look at the densities of lead and mercury. Which one is less dense? So is the lead
Less.
lower density or is the mercury lower density?
I think less density.
Lead is a lower density than mercury. 11,300 something is lower than 13,600. What this means is that when you put a lead ball onto liquid mercury, the lead is going to float. So here's like an old school pool ball that's mostly made out of lead. And normally if you dropped it in like a thing of water, it would just sink straight down to the bottom because it's really heavy. But mercury is even more dense. So the solid lead floats on top of this liquid mercury down here. And it's all due to their different densities. Lead is less dense than mercury, so lead will float on top of mercury. Obviously, solids are more dense overall compared to things like gases and liquids for the most part. And their density tends to be specific to that matter, right? So each element, each compound, each different substance is going to have a different density. One of the cool things about solids is that ice, so solid water, is actually less dense than liquid water. It's one of the few substances in nature that becomes less dense when it is a solid versus a liquid. We're not going to get super into why. It has to do with the way that like the ice crystals form when the H2O molecules bond up with each other. But because of this, ice floats on water. So like whenever you put ice cubes into your drink, right, the ice cubes float on the top of your water or your soda or whatever it is that you're drinking. And that's due to the lower density of ice. It's also why things like lakes and ponds freeze across the top of the lake, and then that ice doesn't like sink down and kill everything underneath it. Because when the ice freezes, it floats on top of the water. So even though this iceberg is huge and ginormous, it still floats in the water because ice, solid water, is less dense than liquid ocean water. There are some other things that can affect density. We've already talked a little bit about temperature. So in general, the warmer that things get, the less dense that they are, whereas colder things tend to be more dense. Pressure can also affect density. Usually, if you increase the pressure of like a container that some substance is in, you can make it more dense. You can fit more substance in there if you up the pressure. And then also another thing I mentioned is that dissolving things in your liquid is going to increase the density. So like this is all salt that's been dried out from ocean water. So because there's all this salt that's dissolved in ocean water, it makes the ocean water more dense than normal like fresh water. All right, so here we have a table of some different substances that all have different densities. So one cool thing to point out is that water, like pure, fresh, clean water, has a density of exactly 1.0. So water is exactly 1 gram per centimeter cubed. That is its density. So everything else is kind of based on, is it less dense or more dense than water? So what I'm going to have you guys help me do is figure out with our different substances over here, are they going to sink or float when you submerge them in water? So I'll start off with an easy one. Air, so like the normal air that's around you that you breathe in, has a density of 0.0013 grams per centimeters cubed. So it still has a density, it still is matter, but it's a gas, so it is a very small density. So is air going to sink or float when you put it in water?
Float.
Float, exactly. That's why all the little bubbles come up to the top when you pop open a soda can. Or why when you like breathe out underwater, if you're swimming, all those air bubbles go up to the top. Because air is very, very light, much more less dense compared to water. So it's going to immediately float up to the top. What about wood? There's all sorts of different kinds of woods, but we'll talk specifically about oak. Wood has a density of approximately 0.85 grams per centimeters cubed. So is wood going to sink or float in water?
It would float.
Float, exactly. 0.85 is lower than our density of 1. So water has a density of 1. Wood has a density of 0.85. So wood is going to float. This is why things like branches or big logs of fallen trees and stuff tend to float along the surface of the water. Most types of trees and plants, their density is a little bit lower than pure water. All right, what about ice down here? Ice has a density of 0.93. So is ice going to sink or float on water?
Float.
Oh, exactly. I was just talking about ice is slightly less dense than liquid water. So 0.93 and 1 are really close in terms of density, but 0.93 is still smaller than 1. So ice is going to float when you mix it in with water. What about aluminum down here? So like the stuff that your soda cans are made out of. Aluminum has a density of approximately 2.7 grams per centimeters cubed. So if you crushed up your soda can into a ball and threw it into a lake, is it most likely going to sink or float?
Sink.
Sink, exactly. 2.7 is bigger than 1. So aluminum is most likely going to sink. What about even heavier metals like lead and gold down here? They've got densities of 11.3 and 19.3. So are they going to sink or float in water?
Sink.
Sink, exactly. 11 and 19 are obviously much bigger than 1. Lead and gold are much more dense compared to liquid water. All right, so finally, what about those guys on the bottom down there? We have ethanol, which is the type of alcohol that we drink in things like beer and wine. And we have methanol, which can be added as like a fuel kind of additive. So are ethanol and methanol going to sink or float if you mix them in water?
Float.
Float, exactly. 0.94 and 0.79 are both smaller than 1. So that's why things like if you ever get a like a flaming shot at a bar somewhere, the reason that they're able to light the top of that shot on fire is because usually they add in an extremely high alcohol content drink like Bacardi 151 or something like that. And that the alcohol in that, it floats on top of the liquid that's in the shot. And so alcohol is very flammable. That's one of its chemical properties. So that's why they're able to light that on fire. And then methanol, that's the reason why sometimes when you see like oil spills or oil slicks in the water and you see all that kind of gross, shiny black stuff floating on top of the water, the reason is that part of it is made up of methanol, which has a lower density than the liquid water that it's mixed with. So very nice job, everybody, especially shout outs to Dewey and Fernando there. So lower density than 1 means that you're going to float when mixed with water, and higher density than 1 means that you'll sink if mixed in water. So you can do this with any 2 substances when you're comparing them. Whichever substance has the lower density is going to float to the top. Whichever substance has the higher density is going to sink to the bottom. So it's all about comparing mass and volume. The ratio between how heavy something is to how much space it takes up is what you need in order to figure out the density of that substance. All right, very nice job, everybody. Does anybody have any final questions about calculating density, what density is, different things that go into affecting density, anything about what we've gone over so far here this afternoon?
No, I don't.
All right, cool. So your homework for today and tomorrow is all about calculating different densities, masses, and volumes. So the one that went up today so you're going to solve each problem for density, mass, or volume. So there's a little example over here to kind of remind you that density equals mass divided by volume. So each of these questions is going to be laid out something like this. A student has a sample of aluminum that has a mass of 27 grams and a volume of 10 centimeters cubed. In order to figure out the density of aluminum, you take the mass of 27 and divide it by the volume of 10. So in this case, aluminum has a density of 2.7 grams per centimeters cubed. So the first several of these have you calculating density. So it gives you mass and volume. It gives you mass and volume. And then the next one changes it up a little bit. It gives you the density of a substance and the volume of a substance and asks you to calculate the mass. So it provided a little hint down here that mass is equal to density times volume. This next one changes it up again a little bit. It gives you the mass and it gives you the density, and it wants you to calculate the volume. So volume is equal to mass divided by density. And then the last two questions on this first worksheet go together. So the first thing that you have to do is it tells you that you've got this rectangular block, and it's a 2 by 3 by 25 centimeter block, and its mass is 600. So the first thing that you have to do is figure out its volume based on these dimensions. So width times height times length. And then use that volume and use the mass that it gives you in order to calculate the density. So density equals whatever the volume is. You take the mass and divide it by that volume.
We have three answer on number 5, or I need to add in 2, 3, and 25 and divide by 600.
Close. So the first question is just about the volume, or number 5, I should say, is just about the volume. And because it tells you the dimensions, all you have to do is multiply these 3 dimensions together. So do the width times the height times the length. That'll give you the volume. And then you got the volume for your answer. You got the mass that it gave to you. So for number 6, you just do the density equation of density equals mass divided by volume in order to figure out the final density of this rectangular block. So you'll use the information in number 5 in order to answer number 6. Good question. And then the assignment for tomorrow is kind of very similar. It's more practice with these density calculations. So it gives you volume and mass and wants you to calculate the density. It gives you the mass, it gives you the volume, calculate the density. It gives you the density, it gives you the mass, and wants you to calculate the volume. Number 4 gives you the density and gives you the volume and wants you to calculate the mass. And then number 5 is the only one that's a little bit different. Number 5 tells you that silver has a density of 10.5 and aluminum has a density of 2.7. And so it gives you the dimension of this metal cube and the mass. And I want you to tell me, based on the density that you can calculate of this little cube, is the density closer to the density of aluminum or to the density of silver? Instead of just telling me what the density is, I want you to tell me, is this metal cube most likely aluminum or most likely silver, based on the density of it that you can calculate? So that is the assignment that'll be going up tomorrow for your Friday daily assignment. All right. Does anybody have any final questions about any of the density homeworks, any of the density questions, or any of the notes about density that so far here today?
No.
All righty. Let me go back to the recording here.